Hello, for Data Communications and Network 1 class today, this is Usana Tantulaves from State University. Today we will talk about the transmission impairment. For this video, I will talk faster, okay? Because it seems to be too many videos now, and this is only chapter 2. Because of the transmission impairment or the problem in the transmission medium, okay, it is impossible, okay, to get the exact pulse shape at the receiver. So suppose you send this as the transmitter, okay, and it go this pulse shape as a square shape, rectangular shape, okay, through the channels, you will receive something like this, okay, at the receiver. It will not be exact same shape. However, for digital communication, okay, we do not need, okay, to receive the perfect one, the perfect shape. We just want to correctly decide whether this is 1 or 0, okay. So if you send 1 with this pulse shape and it gets something like this, and if you send 0 with this pulse shape and it gets something like this, and then you can decide that, oh, this is 1, this is 0 correctly, okay, then this is okay. It doesn't have to be rectangular shape, okay, at the receiving end for digital communication, okay, communication. Now, what are the main source of the transmission impairments? There are the attenuation, which means that the power of the signal will go lower, okay, will reduce the signal power over the transmission distance. Distortion means that the shape is changed, okay, like this, go to this is the shape is changed, okay. And noise is something that added to your signal. This is noise and this is your signal. So you get something like this. Okay, so this is noise. Actually, noise has also multiplicative, but in the undergrad school, we already talk about the additive noise. Attenuation, okay, as I say, the signal strength will reduce, okay, when you send over any transmission medium, okay, over a distance. So you send something, suppose at first the power is like this, and it will go down, okay, with the distance, okay, depend on the medium how fast it go down, okay. You can send through the air or through any wire medium. It's all, the power is all gonna go down. Now how do we increase the signal power or signal strength at the receiving end, okay. For analog signal we use the amplifier. For digital signal we use repeater. What are the difference between the amplifier and the repeater? Okay, let's look at this. This is analog signal, okay, analog signal. You send, okay, over a distance you receive something like this with noise, okay. You have amplifier. You will increase the power of every part of the signal. So it will look like this with the noise, okay. For digital signal, you send this, okay, you receive something like this, suppose. With the repeater, you will decide first, okay, whether this is a 1 or a 0, okay. So suppose you decide this is a 1, so you send out a clear signal, okay, with no noise. You regenerate the signal again, okay, without any noise. So this will be better. This one will be better than this one, right? Than this one, okay, because there is no noise here. Usually the attenuation increases with the frequency of the signal that you are transmitting. So this is the frequency domain in hertz, okay. This is without equalization. So normally if it go up like this is the attenuation in dB. Now, if you, so you can see that with higher frequency, you will reduce, the signal strength will be reduced more. So you can add some equalizer, okay, to make it like kind of less attenuation, okay. So like the attenuation is approximately, the same or similar, okay. So reduce from this line to this line, okay. So it doesn't, the frequency doesn't affect as much without compared with the without equalization. Now for the distortionless system, distortionless means that the pulse does not change shape, right? So what is this condition? Okay, we all want distortionless transmission, but how to get it? Okay, no distortion in the linear time invariant system, LTI. Okay, this is the system that everyone have learned about. We all know about this. Okay, linear time invariant system. You need to have two criteria. Okay, one of them is that the amplitude response must be flat. Okay, so something like this, amplitude response. This is the amplitude response of the system. Okay, in the frequency domain must be flat. Okay, so constant. The phase response must be a linear function of frequency. Okay, or the angle look like this. Okay, TD is the time delay in second. Okay, this is the angle response, look like this. Okay, angle response or the phase response. This is the frequency domain. So it have negative slope. Okay, negative slope. This means that the transmitter will send, okay, intuitively, okay, we send a signal xt, and we get yt. We want yt to be the same as xt, right? As the same as possible as xt. But what we cannot avoid, okay, is that there can be time delay. So you send xt, you get yt, okay? There can be time delay here because it must be a time delay actually, because yt has to happen after xt was transmitted, okay? So the time delay is always positive, and this is what gives you the negative slope for the over here, the negative slope, okay, for the angle. Now, so we have xt, okay, yt is the same shape but with delay, okay, and we also allow it to be scaled because we say that attenuation is reduce the amplitude and reduce the power of the signal, right? So and if you have repeater, amplifier, whatever, you can scale it, right? So k is a constant that make it like bigger or smaller, okay, bigger or smaller shape. So if you send like this and you get something like this, you say it's distortionless system, okay, because it's the same shape with some delay time, and maybe k is less than 1. It's okay. K can be less than 1 or more than 1. Okay. Now, if you compare, okay, you look at the frequency domain of this. This is the time domain that we looked at before, okay? So yt equal to xt with some delay, and it can be scaled up or down. You take Fourier of this, you get, k is the same, xt is xf, and the delay time going to be this phase response here. Now you compare it with the normal linear time invariant system, which is yt equal to ht convolute with the xt, okay, convolution here. Okay, so when you take the Fourier transform, convolution become the multiplier in the frequency domain, right? So you have yf equal to hf multiplied by xf, okay? Now you compare these two systems together, the normal, time invariant system and the distortionless system here. So you compare them together. Okay, so you have, okay, yf is the same, xf is this. Okay, so what do you have left? Hf is this, right? Hf equal to k multiplied by e to the minus j omega td. And td is the time domain, time delay, which is constant. Okay, you must have negative slope here, okay? If it's not negative slope, it means that your time delay is negative, okay? So it's happened before you transmit, you receive before transmit. That is not possible. Okay, so this is the frequency response of the distortionless system. Now let's look at the linear distortion. What is linear distortion? Linear distortion is something that can be compensated, okay, by using an equalizer. You may have heard about equalizer in the music system, that if you buy the equalizer and you adjust the knob, right? and change the sound, okay, to that it sound better. Suppose the frequency response, okay, of the old system is this HF, right? And then you have an equalizer, so you attach equalizer to your system. So the so this is the equalizer, this is the old system. So the frequency response, okay, of the new system is like this, multiply them together, right, in the frequency domain. So you choose HEF or the equalizer frequency response to be, just change this to dy over here, okay, so you get this, okay. So if you do this, it will compensate for the linear distortion and it becomes distortionless system. So suppose your system, okay, has amplitude response like this, okay, so you want your equalizer to be something like this, okay, so that you multiply and then you get, when you multiply together you get H prime F equal to this, okay, frequency response. So you multiply to get this, okay. It can be approximate, okay, in the real system. Now let's look at thermal noise, okay. Thermal noise is due to the random motion of electrons, okay, so it's always there, okay. Electrons just move around and hit each other. It's like the heat, giving out the heat, okay. So thermal noise like depend on the temperature, okay. So if the temperature is not 0 degree Kelvin, okay, you always have thermal noise. So the higher temperature you have more thermal noise, so the formula will depend on the temperature. And thermal noise is a type of white noise. White noise means that the frequency spectrum is constant or flat over all frequency. So it's something like this. You have frequency response, and this is the noise spectral density, power spectral density, okay, this one. Okay, so it can be something like this, constant value, okay, power spectral density. The full name will be on the next slide. Okay, so this one is the worst noise because it cannot be eliminated. It always occurs in all frequencies equally. So if you transmit in this frequency or in this channel, okay, or any channel, okay, you always affected by the same amount of noise for the thermal noise, okay. But it's good in terms of it's easy to calculate, to find the area under curve because it's just constant value, okay. This is a time domain examples of a white Gaussian noise, okay. White noise means that power spectral density is constant in frequency domain. Gaussians mean that the value amplitude is sometimes, go up, go down, like normal distribution, okay. This is the spectrum, okay, if you want to calculate, okay. So actually the noise has value in all frequency, but if you want to transmit your signal in this band, okay, so you want to know how much noise it will affect you, okay, so you can use the power spectral density to calculate, okay, the power in the frequency band that you are transmitting your signal. Power spectral density of white noise, okay, is constant and equal to N0/2, where N0 is equal to K times T watt per hertz. K is the Boltzmann constant, this is the value, and T is the temperature in Kelvin. Now for these examples here, how to calculate, okay, noise power in the frequency band of F1 to F2. This one we write in the also negative and positive values, right, of the frequency. Is KTB or Kung Thai, okay, very easy to remember. K is the Boltzmann constant, T is temperature in Kelvin, and B is the bandwidth, okay, F2 minus F1 in hertz. And how to calculate this? So the height is very simple, right? Height is N0/2, okay, here, okay, so it's the area under curve here, multiply by 2, okay, area under curve, and this is the answer, okay. So you can just multiply them together like this. That's why it's very simple noise to calculate, okay, this one. B is the bandwidth. Impulse noise, okay, the noise spike is a noise spike, okay, that occur unexpectedly. It means it can occur any time that you want. that it wants, okay, and it's a short duration. It has high amplitude, short duration. It's the main source of errors, okay, for digital communications. Why is that? This is a time domain, okay. Look at the 2 microsecond duration spike, okay. For analog voice, do not cause anything, any loss of intelligibility. You still, I mean, it's just 2 microsecond spike of noise, okay. It's just lost in the voice. But for digital data, if you send at very high speed, okay, 1 gigabit per second, this is usually, it's normal right now. So this is 10 to the 9, right, bit per second, multiplied by duration of 10 to the minus 6 seconds, 2 times 10 to the minus 6 seconds. So what you have is the burst error of 2000 bits, okay. So this is affect a lot in the digital communications that we have to deal with. This is a reference if you are concerned with you want to know more about noise. You can look at the white noise and the noise color, like pink noise, brown noise, okay. We will discuss more in class, okay, for the students, okay, with examples, okay. For other audience, thank you very much, okay, for your attention. Thank you.